In this section, we will discuss the inverse normal probability distribution problem. While computing probabilities for normal random variables, we usually start with an x-interval. We then convert this into its corresponding z-score interval. We then determine the area under the curve in this interval, which is the same as the probability of falling in this interval. With the inverse problem, we'll be starting in reverse. We'll begin with a problem which describes an area. We'll then have to determine the z-score interval that corresponds to this area. We'll then convert this interval into the corresponding x values. Let's first go over some inverse basics. Problem A. The area to the right of a mysterious z-score is 0.1. What is the approximate value of this z-score? B. The area to the left of a mysterious z-score is 0.67. What is the approximate value of this z-score? And C. The area to the left of a mysterious z-score is 0.15. What is the approximate value of this z-score? A. The area to the right of a mysterious z-score is 0.1. First, we start by drawing the curve and drawing this mysterious z-score on the right side of the mean. We had to draw the z-score on the right side of the mean because if we attempted to draw the z-score anywhere on the left side of the mean, the area to the right of that z-score would have exceeded 0.5 since it would have contained more than half of the curve. Once we draw the graph with the z-score to the right of the mean and shade in the area to the right of this z-score, let's indicate the fact that the area to the right of this z-score is equal to 0.1. Now, in order to go to our standard normal tables, recall that we must know the area to the left of a z-score. The standard normal table gives the area to the left of a z-score for any z-value that you look up. So you have to know information about the area to the left of a z-score in order to utilize this table. The z-score that has an area to the right of it, which equals 0.1, has an area to the left of it equal to 0.9. We know this because the total area under the curve must equal 1. We should now go to our standard normal tables and look in the area section of the table. Recall, the area section of the table are the 4-digit values that are in the middle of the table. You should never begin by looking up an area by going down the rows or the columns. The rows and the columns here in blue are z-scores that you are looking up. In this case, we are looking for an area to the left of a z-score which is approximately equal to 0.9. If you look over this entire table, you'll find that the closest that we can come to 0.9 in the table. For this problem, we want the closest value. It doesn't matter if the value is slightly above or slightly below. We want the value as close as possible to the area we are seeking, in this case, which is 0.9. The closest area we can find to 0.9 is 0.8997. We should note that this area is in the row for 1.2 and the column for 0.08. This indicates that the area to the left of the z-score 1.28 is equal to approximately 0.9, or in this case 0.8997. Now, we realize that the z-score 1.28 has an area to the left of it, which is approximately 0.9. Therefore, we can conclude that this mysterious z-score is approximately 1.28. Problem B. The area to the left of the mysterious z-score is 0.6700. What is this z-score? We began by drawing our normal curve and placing our z-value to the right of the mean. We decided to place our z-value to the right of the mean because if we had attempted to place the z-value somewhere on the left side of the mean, the area to the left of that z-score would have been less than 0.5, since that area would have contained less than half of the curve. Now that we've decided on how to draw the curve with this z-score being on the right side of the mean, we shade in the area to the left of this z-score and indicate that this area is 0.67. Now that we know the area to the left of our mysterious z-score, we can go to the standard normal chart and look for an area as close as possible to 0.67. In this case, that value is here in the table exactly. We should note that value 0.67, the area 0.67, is in the row for 0.4 and the column for 0.04. Therefore, the z-score 0.44 has an area to the left of it which is equal to 0.67. So the answer to this question is the z-score 0.44 has an area to the left of it which is equal to 0.6700. C. The area to the left of z is 0.15. What is the approximate value of z? Again, we start by drawing our curve and determining that this mysterious z-score has to be drawn to the left of our mean. We know it's on the left of the mean because had we attempted to draw this mysterious z-score on the right side of the mean, the area to the left of that z-score would have been greater than 0.5 since it would have contained more than half of the curve. Now, we indicate that this area to the left of our mysterious z-score is equal to 0.15. If we go to our standard normal table and look for the area in this chart as close as possible to 0.15, we'll find that 0.1492 is the closest that we can come to 0.15. This area is in the row for -1 and the column for 0.04. Therefore, the z-score -1.04 has an area to the left of it which is equal to 0.1492 or approximately 0.15. So the z-score -1.04 has an area to the left of it which is approximately 0.15. Now that we've learned some inverse basics, let's try to put the whole inverse problem together. Student grades in Dr. Nutty Professor's class are normally distributed with a mean of 70 and a standard deviation of 10. A. The professor decided that he would assign A grades to students in the top 15% of the class. What is the lowest A grade that he assigned? And B, the professor decided that he would assign F grades to students in the bottom 10% of the class. What is the highest F grade that he defined? This is our inverse problem. In this problem, we've described an area. After we draw that area, we'll figure out the z-score interval which corresponds to this area, and then we'll convert this into its corresponding x values. We start by drawing the curve, and because the professor said that the students were in the top 15% of the class that would receive A's, we start by drawing the top part of our normal distribution curve and indicating that its area is 0.15. We now need to determine the z-score, which corresponds to have an area to the right of it equal to 0.15. Recall, in order for us to go to the standard normal table, we have to know the area to the left of a z-score. Since the area under the entire curve is equal to 1, we know that the area to the left of our mysterious z-score must be 0.85. If we go to our standard normal chart and search for the area 0.85, we'll find that the area 0.8508 is the closest that we can come to 0.85. This area has a corresponding z-score which is equal to 1.04. Therefore, the z-score 1.04 has an upper tail area which is equal to 0.15. Now that we know the z-score that corresponds to this area, we need to use the z-score formula and plug in all of the information that we know in order to determine the corresponding x value. For this problem, we know that the z-score is 1.04. We don't know the x value. We know that the mean for this problem is 70, and we know the standard deviation is equal to 10. If we solve this problem for x using basic algebra, we will find that x is equal to 80.4. Therefore, the x value that corresponds to the z-score 1.04 is equal to 80.4. The lowest A grade, which corresponds to the top 15% of the class, would be a grade of 80.4 or higher. Example 1b. We need to determine the highest F grade that the professor would assign, that grade that corresponds to being in the bottom 10% of the class. We start by drawing our graph and shading in the bottom tail of our graph to represent the lowest 10% of the graph. We then go to our standard normal table and look in the 4-digit area section of the table to find the area as close as possible to 0.1000. If we look in the table, we'll find 0.1003 is the closest that we can come to an area of 0.1. This area has a corresponding z-score of negative 1.28. Now that we know our z-score interval, we need to determine the x value or x interval that corresponds to this. Using our z-score formula, we plug in the z-score negative 1.28. We don't know our x value. We plug in 70 for our mean and 10 for our standard deviation. If we solve this problem for x, we'll find that x is equal to 57.2. Therefore, students in this class that are in the bottom 10% would be grades that are 57.2 or below. So the highest F grade in the course would be a 57.2. Now let's get some hands-on practice with the inverse problem. The weights of students at a local high school are normally distributed with a mean of 125 pounds and a standard deviation of 15 pounds. What weight defines the 80th percentile? In other words, determine the weight in which 80% of the students weigh this amount or less. You should pause the video at this time and try to complete this problem. You should have started by shading in the area under the function which corresponds to the 80th percentile, or the weight such that 80% of the values are this value or less. You should have then indicated that this area represents an area of 0.8000. Next, you should have went to the standard normal probability table and tried to find an area as close as possible to the area 0.8000. Remember, you should be looking in the 4-digit area section of the standard normal table. If you looked in the chart, you would have found that the closest that you could come to this area was an area of 0.7995. This area had a corresponding z-score of 0.84. If we use our z-score formula and plug in 0.84 for our z-score, we don't know our x value, plug in 125 as our mean and 15 as our standard deviation, and then solve for x, we'll find that x equals 137.6 pounds. Therefore, 137.6 pounds represents the 80th percentile for the weight of students at this school.